We're going to continue today with where we left off last week. So keeping with our core programming concepts, I think we left off at arrays. So an array, just to recap, is an object which is an ordered collection of things. It's delineated with an enclosure of square brackets. Let's just create an array and put some things inside of it like this. So we have an array stored in the interpreter variable x. And it doesn't have to be numbers. In this case, it's a mix of floats and integers, but you can put whatever you want inside an array, even other arrays. Right? It gets pretty wild sometimes. So how do we deal with arrays? There's a couple of methods that are good to know right off the bat. One is, how big is the array? This one has size 6. I think I probably covered some of this last week, but so it might be a little bit of overlap. But and we can access, I think I did this as well, access an item by index. And there are two syntax styles for doing this. And the main thing to keep in mind is that the first item in the array has index 0, not 1. So this will give us the integer 12, which is stored at index 2. I believe, let's see if I do this correct, we can even request an array of indices, something like this. We've got the double square brackets here. So this is saying, give me an array containing the items stored at indices 1, 3, and 4. So I think this should return the array 7, -4.5, and 0. So you can be very specific with accessing and retrieving certain items in an array. So this is kind of fundamental array manipulation. And we can always create the array by just writing it out like this. But what if we want an array containing all of the numbers from 0 to 1,000? We're going to write those out? Absolutely not. No way. Right? So there are a couple of syntax shortcuts which make it very easy to create large arrays that are in some way procedurally or algorithmically generated. So the example I just gave, we can say x equals, and then parentheses, 0, ... 1,000. And this is a shortcut that says, give me an array that starts at 0 and goes all the way to 1,000. It's not even going to print everything, but this is just the post window saying, you get the idea, you can imagine the rest. Sure enough, this is an array which has 1,001 items in it, right? 0 to 1,000. Instead of this syntactical approach, we can actually use the array class and use one of several array creation methods. So series is the closest approximation here, which says how big of an array do you want, where do you want it to start, and what do you want the increment to be. So give me an array of 1,001 items starting at 0 and going up by 1 each time, and this gives us the same thing. If we change this to a 2, it's going to start at 0 and skip every other number, so all even numbers. We can jump by 7, so multiples of 7. There's even a syntax shortcut for this. We can say 0, 2, ... And this is very similar. It's going to start at 0. The item at index 1 is going to be 2, and then it's going to follow that pattern until it reaches or exceed, or it's not going to exceed this maximum here. So that'll give us the array, right, 0, 2, 4. Maybe this 1,000 is a little bit hard to be. Let's make it a little bit smaller. Let's go down to 100, just so we can actually see everything in the post window. Right. So that's every integer, 0 to 100, and just evens. You get the idea. You can even go in the opposite direction, like this. But you want to be careful not to do something that doesn't make sense, because here we'll start at 100, go down by 2s, and we're telling it to stop at 200, but that's not going to work. So it has to make sense. Other array creation methods, there's array.geom, which is an abbreviation for a geometric series. This is the same as series, but instead of addition, it's multiplication. Say 10, size 10, start at 2, multiply by 2 every time. So we start at 2, multiply that by 2, multiply that by 2. So this could be useful, for example, when dealing with amplitudes. If we want to reduce the amplitude by half every time, or something like that. We can go the other way, divide by 2 each time. What else do we have? Array.rand. It's going to give us 10 random values between 100 and 200. So that's just to give you a taste of some of the ways we can create arrays. Here's a question. Let's say we have this array, and we say x plus 5. So the array x contains 3 items, 100, 200, 300, and we're saying add 5 to this. What does this mean? Right? It's not immediately clear, right? This is an operation that could be defined in a number of different ways. And when you're designing a programming language, these are the kinds of questions you have to answer. Like, what does the user mean, most likely, when they type this? So the way it's defined, when you apply a binary operation with a single value and an array, presumably of values, it's going to apply the operation to every item in the array. And this is actually what we want, because as we'll see down the road, we use arrays to represent multi-channel signals. Like a stereo signal is an array of 2 signals. And when we want to scale the amplitude, we might multiply it by some value like 0.5, and we want that to apply to both channels. So this is a very useful way to define this type of operation. Same applies for all sorts of binary operations, right? So multiplication, division, anything like this. What about something like this? So we have an array of 3 things and an array of 3 things, and we're going to add them together. You might be able to guess how this is defined. The operation is applied to corresponding pairs of items. So this is going to give us 105, 206, 307. And if one of these is a different size than the other, well, now again we have to say what actually is going on here. Are we allowed to do this? Right? Is it going to say array size doesn't match? Can't do it. What happens here is something called wrapping, W-R-A-P-P-I-N-G. And so it starts out with corresponding pairs, 100 plus 5, 200 plus 6, 300 plus 7, and it doesn't have something here to add to the 8, so it goes back to the beginning. And it's going to start over and get 108 for the last value. So if there's a shorter array, it's just going to keep repeating itself until it accommodates the larger array. And that is how, in a nutshell, binary operations work with arrays. And this will show up again. Now the last thing I want to show with arrays is a method called dupe, which is short for duplication. And we could take any object, like the string hi, and say .dupe, and then we provide some number. This is going to return an array that contains 4 copies of the receiver. Now you don't see the quotes here, but these are in fact strings, right? We just don't show them for conciseness, I guess. We can say the number 7.7, right? And we have an array containing 4 copies. And we can put whatever we want here, 9 copies. This is a really fast way to create an array if you just want it to contain a bunch of stuff, copies of a thing. And there's even a syntax shortcut, which is the exclamation point. Right? So 4.dupe9, 4 exclamation point 9. So this is actually a binary operator, just like addition and subtraction. It's just a symbol which represents an operation involving 2 things, and it returns an array of size, the second thing, containing copies of the first thing. Again, we will see this exclamation point again and again and again. It's a great way to take a mono signal and just turn it into a 2-channel signal. Just copy that signal, play it in the second speaker as well. Okay, and on the course website, I've uploaded an array cheat sheet because there's a lot more to talk about with arrays. That is over here, and just a bunch of code and examples and comments where you can browse and try each one and interact with them, change the numbers, see how it works. So do check it out. Okay, so that's arrays. Now I'm going to move on to functions. What is a function? A function is a device which lets us encapsulate some block of code and define it, give it a variable name, and in doing so, we make that code a little modular unit that we can reuse throughout our code without having to rewrite the function or copy and paste it. So in the course of using SuperCollider, you're going to inevitably come up with little functions which perform some task that you might want to perform again and again and again. So that's always a good opportunity to create a function from that code, give it a name so that you can properly reuse it whenever you want. Let's look at a really stupid example first. Okay? So the expression 2 plus 3. Right? Let's imagine this is some useful function that does something really magical. And we want to say, OK, I'm tired of typing 2 plus 3 over and over again. So we're going to say some variable name, we'll say capital F, equals that code enclosed in curly braces. And in doing so, we're no longer returning the number 5. We're returning this little black box called a function. And when we evaluate this, the interpreter does not look inside the function. It sees the curly braces and says, OK, there's something in there. I've got it. And you let me know when you want me to look inside. So right now, we've just defined the function. And to evaluate it, we say the name of the function dot value. And you can provide parentheses here if you want. You don't have to. And this says, OK, actually look inside the function, evaluate the code, and the value that it returns, store it in this variable. And so now x is equal to 5. It's a really stupid example. Right? It's on no planet would you ever need to save 2 plus 3 in a function. Usually it's something much more useful. But this is the gist of it. You can also say f period open and close parentheses. This is a shortcut for calling value on a function. I really like this. I'm trying to adopt this sort of completely because it's very nice and short. All right, and all right. So let's look at a more interesting example, a slightly more interesting example. I think on the homework, the last question of your homework, I asked you to build a function that converts pitch letter names into MIDI note numbers. So that's an example of something which actually has some real value to it. So let's say we want to make a function that, let's see, cubes a value and then subtracts 1. Right? So if we start with the value 5, we could say something like this. So we have a function which declares a local variable, sets it equal to 5, sets it equal to the cube of itself, and then subtracts 1 and stores the result. And functions, when you evaluate a function, the thing that gets returned is always the value of the last line. There's no need to explicitly say, return this value. It's assumed that the last statement is going to be the value that comes out of a function when you evaluate it. So now we can say f period parentheses, and we get the result of 5 cubed minus 1. All right, so the next obvious question is, how do we put an arbitrary value here? We don't always want to cube and subtract 1 from 5. We want to be able to specify the value that gets cubed and minus 1 when we call the function. So to do this, we introduce the concept of arguments. So an argument is declared, you can only declare arguments at the very beginning of a function. They're a function-specific device. So here's one way to do it. We say, here's an argument. Let's call this input, just for clarity. And we'll say var output. So the output is going to be the input cubed minus 1. Something like that. I'm just rewriting this. There's many ways to structure this. I previously had this step and this step on separate lines. Now I'm combining them into one. It's really kind of just a matter of style and taste. So this function has an argument named input. And if we just evaluate it as is, it's going to use this default value of 5. So we'll get the same result. But the argument is not just a container that holds data. It's a device that lets us pass a value into the function when we call it. And we do that by putting a number in these parentheses. So this expression means evaluate the function, passing in a value of 4 for the argument. So this will return 4 cubed minus 1. We can put whatever we want in here. 1 cubed minus 1. Negative 7 cubed minus 1, etc. There's a syntax shortcut where instead of typing arg, you can just put a set of what are called pipes, these vertical bars. It's the key right above your return key. And this is just a syntax alternative, so same idea. If you have multiple arguments, like this, here we cube it and then subtract some additional value which we can determine when we call the function. All right, so here by default the input value is going to be 5 and the value we subtract is going to be 1. And so what we can do now is say 4, 2. So this is going to say the input value is 4, the diff value is 2, so we get 62, 61, right? There's 5 cubed minus 5, 5 cubed minus 6. So the values we provide here are going to be plugged into the arguments in the same order that they're declared. And that's kind of it on functions. And there's really not too much else. The arguments are containers that allow you to pass values into the function. And then variables, which have to be declared immediately after the arguments, are just more generic containers for holding data. I mean, we don't even really need the variable here. We could just do this, and it would return the last statement. But with larger functions, you probably have a lot of different named things that you want to keep track of. So it's always good to declare variables, give everything a name, and write things out in a way which is really clear and understandable. Make sense? Okay. A quick little detour on a topic called literals. There's a reference file named literals. Normally, in most cases, when we're using SuperCollider and we want to, work with information in some way, like we want to create a new graphical window, right? Like imagine we're doing some graphical user interface design. We say window.new. So we take the class, we use a method, usually new, which says return a new instance of this class and store it in W. And then we can say, we talk to the instance itself. We apply additional methods to the instance of the class that was returned. So now W is an actual instance of a window, and we can say front, which makes it appear. Window is not a literal class. What is a literal class? A literal class is a class that has a direct syntactical representation, like numbers. Right? There is a class of objects called integer, and there's also float and array and string and symbol, but all of these classes are literals in the sense that we don't have to say, integer.new just to make the number 5. Imagine, that'd be so ridiculous, right? If we had to say, okay, we got to make a number here, integer.new 5. This is ridiculous, right? There's absolutely no need to do this because we already have a standard set of symbols to represent numbers. So that's what we mean when we say a literal. Arrays too have a literal representation, although there is a sort of a distinction between literal arrays and non-literal arrays. But the main point I'm trying to make here is that the classes we're covering are, for the most part, literals. But this is not usually the case once we really get going. We're going to be saying, x equals class.new, and this.new, that.new. We're going to be making new instances because we don't have a symbol in the ASCII character set that represents graphical windows or like sine oscillators and white noise generators. Right? We can't do a syntactic representation of that thing. We have to be a little bit more abstract and say, this.new, that.new. So that's just want to make a distinction there. It's not something you really need to understand at a deep level. It's just that for the most part, we're going to be doing stuff like this rather than just typing out explicit things. All right, moving on to a few more concepts in the remainder of this core programming concepts lecture. I want to talk about randomness. There is a guide file called Randomness, which you can browse for all sorts of options for creating random numbers. Randomness can be really nice and attractive in music. Right? We want to have pitches in a scale or a collection, and instead of having to compose them out, we can just say, computer, you handle it. Right? Pick some random numbers. So some simple ways of generating random numbers is two methods, rrand and xparand. This rrand is short for ranged random. You give it a minimum and a maximum, and it will return a value within this range, including its boundaries. So it could be anywhere from 1 to 10. If both the min and the max are integers, the result will be an integer. But if either of these is a float, the result will be a float. Xparand always returns floats. Doesn't matter what the min and max are. But the difference between rrand and xparand primarily is that rrand exhibits a uniform distribution. So every value in the range is equally likely to be chosen. Xparand approximates an exponential distribution. So if you imagine the curve, x squared or 2 to the power of x, or some one of those exponential curves like that. That curve acts as a sort of mapping function. So values come in on the x-axis and come out on the y-axis. So most of them are going to get sort of pushed down towards the lower boundary. So if we just say 1 to 1,000, you'll notice that most of these values tend to be relatively low, right? Like that's not a uniform distribution from 1 to 1,000. There's no way we're going to get 5 of these in a row. So this is exponential behavior. So low values, and it's going to be pretty rare for us to get something up towards 1,000. Like I'm not seeing any 800s or 900s. There's one, but it's not very common. What's the point of these two methods here? Why do we need a uniform and an exponential distribution? Anyone know?
Because frequencies are on an exponential scale.
Yes, right. Frequency, for example, we perceive pitch logarithmically. Right? So if we go up by octaves, the frequency actually doubles each time. So this means if we were to, let's say pick a random frequency between 20 and 20,000 using rrand, then about half the time it's going to be between 10,000 and 20,000, and that's just one octave, and it's a really annoyingly high octave. So that's not a good idea because all these frequencies are going to basically sound the same, just like really high-pitched tones. But xparand approximates this exponential distribution, which means it's going to be a uniform distribution of octaves. Like we're equally likely to get something between 20 and 40 versus 40 and 80, 80 and 160, etc. So this is going to be a lot more balanced, air quotes, balanced. Similar with amplitude. Right? If we did a random number between 0 and 1, half the time it's going to be between 0.5 and 1, and that's just a 6 decibel difference. But between 0 and 0.5, that's from -6 down to -infinity decibels. So again, exponential makes more sense there. But if you're working explicitly with decibels, if you want to be somewhere between -80 and -10 decibels, then this uniform distribution makes more sense. So it depends on what the values are going to be used for. Sometimes exponential makes sense, and sometimes uniform distribution makes sense. Okay, other random options. We don't always want to pick a value from a range. Sometimes, like for example, you pick a value from a diatonic musical scale, right? You would represent that with if semitones, you'd represent that with 0, 2, 4, 5, 7, 9, 11, right? It's sort of a C major scale. So to do that, we can just create a collection for ourselves like this. I forgot a comma. Right. and we can say .choose. And this will pick a random value from that collection. It doesn't modify the collection. X remains untouched. Choose is just going in and randomly indexing something and saying, here you go. Right? Just making a little copy of it and reporting back to us. And if you want, another thing we want to do sometimes is make a choice, but unevenly distribute the probabilities of making a particular choice. Maybe we want to, let's just say we have, C, E, and G or something like that. And we want to pick C 70% of the time. E, I should just call these numbers. They're not C, E, and G. This is 0, 2, and 4. Let's say we want to pick 0 70% of the time. The number 2, 20% of the time. And the number 4, 10% of the time. Right? One stupid way to do this is to just, do the weights yourself, like this. And then just say choose, and then you've kind of baked those probabilities directly into the array. But we don't have to do this. This is manageable, but it does not scale. We can't apply this uniformly. So instead, we can say wchoose and provide a same size array of weight values, weight, and they have to sum to equal 1. Like this. So we have our array, and we say pick with the following probabilities. Yeah, so we're getting a couple of 2s and 4s, but mostly 0s. There's a lot of situations, I find myself in a lot of situations where I have a lot of numbers, and I really don't feel like pausing and going over here and deriving some array that sums to 1. If it doesn't sum to 1, the probabilities get messed up. I'm not exactly sure what goes on under the hood, but it doesn't work correctly. So if you just want to say, just pick some kind of random values that like loosely approximate the probabilities you want, you can then append .normalize sum. And what this will do to its receiver is scale all of the values proportionally so that they sum to 1 while preserving their ratios relative to each other. So here we go. Now we've done the same thing, and we can't really see the percentages unless we evaluate the normalized array, but it's 64% of the time it's picking 0, 24% of the time picking 2, and 12% of the time it's picking 4. Okay, and then one last bit on randomness. What if we want to generate not a single random number, which is what we've been doing with all these evaluations, but we want to generate a collection of random numbers. Okay, so one thing we might try is something like this. So we're going to say a random number 1 through 10 and make 8 copies. But this doesn't quite do what we want. It doesn't seem very random, does it? Neither does that. So maybe you can sort of figure out what's happening here is when this method is called, this method rrand, it returns a value. And then it applies this binary operator to that value. Things are evaluated left to right. So we don't actually get 8 uniquely chosen values. We just get one random value and 8 copies of it. How do we fix this? The trick is to duplicate a function containing the code that you want to be duplicated. And functions respond to duplication with a slightly different behavior than other objects. Other objects just kind of duplicate themselves. When you duplicate a function, the function is evaluated once for each item that populates the array. So it's not just going to put, it would be really kind of stupid if the result of this was an array of a function, we don't want that. We want random numbers. So the functions are defined to respond to duplication by not just duplicating themselves, but duplicating themselves and evaluating themselves. So this will give us an array of 8 properly, uniquely random numbers. And every time we do it, we get a new random number. So you can put any code in here. You can put this kind of thing, right? And it's going to evaluate this code 8 times to create this array. Right, so that is the trick. One thing you might want to be careful of is like if you wanted to create this random array and then shift it up an octave by adding 12. You can do it this way. That works fine. But I think if you put it here, some weird stuff happens. And if you think back to week 1, this is because binary operators like plus and exclamation point, these are applied left to right. So the first thing that happens is 12 plus a function. And we're kind of back to talking about a number plus an array. It's like, how is that defined, right? With arrays, we just apply the operation with the number and each item in the function. But this is or each item in the array, excuse me. But now we have a number plus a function, and SuperCollider does this thing where it says, okay, I've composed a new function. It's doing some clever things under the hood here, which is not really what we want it to do. So I'm only bringing this up as a reminder about order of operations and to use parentheses to guarantee certain things happen first. You want to make the array, then add 12. So that'll work just fine. Okay, so next we have 2 more topics I want to get to. The first is conditional logic. And this is in a help file called control structures. Conditional logic refers to programming tools that allow us to make choices depending on whether certain conditions are met. Like if the amplitude is greater than 0.5, do this. Otherwise, do that. It's a branching operation. Instead of doing the same thing every time, you check some condition. And so we're, I think, revisiting the idea of Boolean values here, which are true and false. There's exactly 2 Boolean values, true and false. And conditional logic, well, these are methods, a collection of methods which check some Boolean expression, some expression of code that returns either true or false, and then will perform one of 2 functions based on the results of that outcome. And this is where the receiver dot method and method receiver syntax starts to get a little bit confusing looking, I think, if you pick a certain route. I mean, we in randomness we introduced rrand, and the receiver.method version of this would look like -80.rrand -10. And this is syntactically equivalent, right? This is functionally equivalent, but a syntactical variation. And I prefer this approach because I think it highlights the ranged nature of this more clearly. And something similar happens with if, where I like to put the method first because then it looks like an actual English sentence. If something, 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 something. Right? So it's going to look like this. If takes a Boolean expression followed by a function to be evaluated if true, and a function to be evaluated if false. So let's say x equals 0, 1, dot choose, and then we will do our if statement. So if x equals 0, this is another binary operator which, imagine it as an equal sign with a question mark over it. Right? It equals, right? You're checking for equality. It's not the assignment operator. This says store 0 in the variable x. This asks, is x equal to 0? Very common source of weird stuff happening in your code when you forget to do the conditional operator here. Let's say we're like flipping a coin or something here. Okay, so we flip a coin. 0 is heads, 1 is tails, and we're going to check here and say, okay, so we got heads. We could even post this as well. So we got a 0, that's heads. Got a 1, that's tails. Other types of binary operators that return Booleans. This is equality. There is exclamation point equals, which is not equal. And you're asking, is 1 not equal to 2? That is true. Greater than, less than, and there's also greater than or equal to, and less than or equal to. So this would be true, because 1 is, yes, question.
Whenever you have, does 0 and 1, like the numbers, also evaluate to Booleans if it's in an if statement or no?
I think you have to say as Boolean. And you can say as integer as well. So you can convert back and forth with Booleans and integers using as Boolean and as integer. But the conditional check here, I believe, must return an actual Boolean. If it returns like a 1, yeah, it says non-Boolean. 1 is not a Boolean value, but we can convert it to 1. We convert it to a Boolean. Yeah, good question. All right, sometimes we want to check multiple conditions, like when you go to the grocery store and you check, do they have ice cream? No, do they have chocolate ice cream? And is it on sale? Right? Then I'm definitely going to buy some chocolate ice cream. Something like that. So we want, let's say we have, we're flipping 2 coins here. And we want to, post double tails if they're both 1. So the expression here would look like x equals 1. And if you want to use the method, you can say dot and then provide the other one, like this. So that is one way of expressing x is equal to 1 and y is equal to 1. Or you can use the binary operator double ampersand. And we'll say nope over here. So there we go. That's 2 heads. There we go. If you want to do or, so it's a double pipe. That's the symbolic operator for or you can say dot or. So here, as long as we get at least 1 tails, then that will be considered, this expression will be considered true. Right? So there's and there's or. When using the symbolic operator, these parentheses are 100% needed, because we run into a similar problem again if we just write it like this, because it's going to go left to right, binary operators. It's going to say x equal to 1. That's going to return some value, true or false. Then it's going to say and some integer, right? True and 1. What? Doesn't make any sense. I think this is going to, I'm not sure what is going on here, but it's always, well, trust me, this will mess you up. Sometimes it doesn't give you an error, and sometimes it looks like it's even working correctly. But I think if you were to do, well, maybe I'll come up with a way to mess this up. But in like half the time, if you forget the parentheses, it's going to say non-Boolean in test or some other crazy looking error. So you've really got to make sure that the conditional expressions, the Boolean expressions evaluate first, and then we apply the and or the or. So it's a little bit, it's frustrating sometimes, the left to right precedence, because it makes, you have to use parentheses and you get some unexpected results sometimes, but this is the way it should look. For consistency, we'll keep it like that, because at least 1 tails. Okay, and then finally, I think we have just enough time to wrap up core programming concepts. The last thing I want to talk about is iteration. Iteration refers to tools and techniques that allow you to express repetitive actions concisely. Let's see. So if we want to, let's say we have an array of random numbers, right? 20 random numbers, and we want to figure out how many of them are prime numbers or something like that. Right? Now we can say is prime on a number. That's perfectly fine. But x, which is this array of numbers, it doesn't like that. Right? Some methods like squared arrays are perfectly happy to receive those methods, and we'll apply them to each. But is prime for some reason doesn't work that way. And so what do we do here, right? I want to figure out if each one of these numbers is prime, and I don't want to have to say x at 0. And okay, that one is prime. Great. Next. Right, this is slow and tedious. It's repetitive. Anytime you encounter some sort of repetitive task in a programming language, if you find yourself pasting code, copying and pasting many times, or just doing something over and over again, almost 100% of the time, that job can be made a lot simpler using some sort of iteration method. So there are two methods I want to introduce, do and collect. They're almost the same. They have a slight difference between them. Both of these methods are applied to an array or some type of collection. It doesn't have to be an array, but usually some collection type object. And do and collect each take a single argument, which is a function. And that function will be evaluated once for every item in the collection. So we might temporarily abandon this isPrime method. Maybe that's not the most instructive thing, but let's still use our collection x. And we're going to say x.do, and then a function, which will say right? So we run this. Do will iterate over x, and for each item in x, it's going to evaluate this function, which posts the string, and it happens 20 times because there are 20 objects in x. Now this is, like our function example, really kind of stupid, right? Why would we do this, right? It's not useful. Maybe we want to, add 100 to each number. So we can say x, let's see. Oh, well, actually, the first step is we need to actually pull the values from the array into the function. And the way we do that, should come as no surprise, we declare a variable. So we'll do a little argument declaration. Of course, you can also do this. And we'll say num plus 100.postln. And what we get is 7115, etc., but it posts 100 plus that value each time. So just to when I first learned iteration, like back in 10, 12 years ago, I found it to be a real brain twister. Just the way it's expressed here and the actual action that it ends up doing, it takes time to digest if this is fully new to you. And it takes time to kind of fully realize the kinds of situations in which this is incredibly useful. But what's happening here is we have some collection, and we do this function for each item in the array. We pass in each item as iteration occurs. So first 7 comes in, then 1, then 5, and gets plugged into this function, and we post the result of that number plus 100. Collect is almost the same, but the difference is in what they return. Do returns its receiver. So this, we get a bunch of posted stuff, but ultimately what gets returned is x. So y is just basically a copy of x. Now the point here is that you don't really use do when you want to capture some modified version of the receiver, because do doesn't change its receiver. Do is much more useful if you just want to do something a bunch of times, like make a sound, right? Or just have some action, make a window, move a slider, some sort of action item, which doesn't return something of value, but performs some action that we care about. So do is great for that, because we can just say, here, for this many things, do this. Collect returns a modified receiver based on what the function returns. So when we collect over x, we pass in each item. We don't even need to post them. We could if we wanted to. It doesn't really matter. And what's going to be returned by collect is a new array of the same size in which each item is the result of the corresponding evaluation. So we'll do this, we post a bunch of stuff, and if we check the value of y, it's actually also posted in the post window, it is a new collection that has been derived from x, but is different. So now we can bring back our isPrime method. Right? So now we get an array of booleans, right? To say, which ones are prime and which ones are not prime. A couple of shortcuts here. If you just want to do some action a bunch of times, like, post the string, posting's fun. You don't have to make, if you want to post this, or just perform some action 20 times, you don't have to make an array of 20 things. You can also just say 20.do. And do is defined for integers to treat it as if it were the array 0 through 19. So we could even declare an argument, and we'll append the number to the string. So now we'll get the string concatenated with the number itself. In do and collect, you actually get to define 2 arguments. And let's go back to our random number example here. So let's copy this, bring it down here. We're going to declare 2 arguments, num and index. And again, you can name these whatever you want. But no matter what they're named, what they represent is the item in the collection, sort of one by one, and the index of that item in the collection, one by one. So if we just post these, we'll see that what we get is the item and its index, the item and its index, the item and its index. So this means inside of an iteration function with do or collect, we can give ourselves access to the items themselves, what their values are, and what their indices are. And this can be useful in a variety of cases. And I may try to cook up some additional examples and maybe put them on the next homework or something like that, just to really make sure everybody sort of gets this into their brains. So I know this is a bit abstract, these examples. They don't really seem to have any sort of context. They're just kind of arbitrary actions. But I hope you'll trust me when I say that as we get going with sound and synthesis and things like that, these iteration methods come in handy. If you want to make 200 oscillators with random frequencies, collect is fantastic for that. Right? You just collect over a bunch of frequencies and return oscillators that contain those frequencies. It's really the possibilities in terms of sound, really, they go on and on and on. So, okay, and we are just about out of time. So that wraps it up for the first unit. There's the homework is due before class Thursday next week, and we are going to start making sound next week. So thanks all, and see you then.